Welcome, everyone, to our session on leading data science projects and teams. Our primary objective today is to equip you with the knowledge and skills necessary to confidently lead a data science project or team. By the end of this course, you will have a strong foundation in key data science concepts, allowing you to oversee projects from start to finish with a clear understanding of each step involved. We will start by covering what a model is in the context of data science. We will then look at the work required to prepare data for modeling. Once we have our data, we'll understand what training the model means. We will then discuss different types of problems and the models we may use to solve them. Finally, we'll discuss how we measure and improve the accuracy of our models. Data science is an interdisciplinary field that leverages a combination of statistics, computer science, and domain knowledge to analyze and interpret complex data sets. At its core, data science involves collecting and preparing data, applying analytical and computational techniques, and deriving insights that can inform decision-making and strategic planning. This process often includes a range of activities such as data cleaning, exploratory data analysis, and the application of machine learning algorithms to uncover patterns and make predictions. The primary reason for engaging in data science is to transform raw data into actionable insights that can drive better decision making and solve real world problems. Organizations use data science to identify trends, forecast future outcomes, and optimize operations. For example, businesses might use data science to understand customer behavior, improve marketing strategies, or enhance product recommendations. In essence, data science helps in making informed decisions by providing a deeper understanding of data, which can lead to more efficient processes, better products, and competitive advantages. In this part of the course, we'll explore the fundamental concept of models in data science. Models are essential tools that help us understand, interpret, and predict various phenomena using data. They serve as simplified representations of reality, allowing us to make informed decisions and gain valuable insights. In the simplest terms, a model in machine learning is a computer program that learns from data to help us make better decisions. Let's break down what this means with some easy to understand examples. Predicting future events. A model can help us predict what might happen in the future. For example, a business might use a model to predict if a customer is likely to cancel their contract. By analyzing past data about customer behavior, the model learns patterns and signals that often lead to cancellations. This way, the business can take action to retain the customer before they cancel. Identifying patterns. A model can help us recognize patterns in data that might not be obvious at first glance. For instance, in healthcare, a model might be used to identify early warning signs of a given illness. By examining patient data, the model can spot subtle signs that indicate the onset of the illness, allowing for early intervention and treatment. Making decisions. Sometimes a model is a collection of rules that helps us make decisions. For example, a bank might use a decision tree model to decide whether to loan money to a client. The decision tree is a series of if-then rules that the model has learned from past loan data. It helps the bank systematically evaluate the risk of lending to a particular client. Extracting information from text. A model can also be a tool that helps us understand and extract information from text. For example, a model might analyze customer reviews to determine common themes and sentiments. It can systematically read through thousands of reviews and summarize the main points, such as identifying frequently mentioned product features and overall customer satisfaction. But no matter the specific task, a model is always a computer program that learns from our data to help us make better decisions. It uses the information we've provided to understand patterns, make predictions, and guide us in making informed choices. Many people might not realize it, but AI models are a significant part of our everyday lives, seamlessly integrating into various services and tools we use daily. Let's take a closer look at some common examples. First, consider spam filters in your email. Every time you receive an email, AI models analyze the content to determine whether it's spam or not. These models learn from millions of emails, recognizing patterns and characteristics of spam messages to keep your inbox clean. Next, let's talk about voice recognition technologies like Alexa. When you ask Alexa a question or give a command, an AI model processes your voice, understands the request, and provides a response. This involves complex models trained on vast amounts of voice data to accurately understand and react to different accents, dialects, and languages. Netflix recommendations are another excellent example. As you watch movies and shows, AI models analyze your viewing habits and preferences. These models compare your behavior with millions of other users to suggest content you're likely to enjoy, enhancing your viewing experience. Google Maps relies heavily on AI for real-time traffic updates and route planning. AI models process data from various sources, including user location data, road sensors, and historical traffic patterns to provide you with the fastest route and real-time traffic conditions, helping you navigate efficiently. On Instagram, your personalized feed is curated by AI models. These models analyze your interactions, such as likes, comments, and follows, to show you content that aligns with your interests. This personalization keeps you engaged and ensures you see posts that are most relevant to you. Lastly, consider your online bank, which uses AI models to identify suspicious activity. These models monitor your transaction patterns and flag unusual behavior, such as unexpected large withdrawals or transactions from distant locations, to protect you from potential fraud. As you can see, AI models are deeply embedded in the services we use daily, making our lives more convenient, personalized, and secure. They work behind the scenes, learning from data to improve their performance and provide us with better experiences. So, what is a model? Well, providing a single explanation is tough. Models are used for a variety of things, and as a result, differ in many ways, as we saw through your own use of models in your day-to-day life. Some models are used to predict, some forecast, and some find patterns in data to help us cluster or segment things. While a definition is hard, we can say that a machine learning model always learns from data in order to give us a benefit. Let's move on to the next section, where we will start looking at the types of model, which will help reinforce this point. In this section, we'll delve into the various types of models used in data science. Understanding the different modeling approaches is crucial for leveraging data effectively in your managerial decisions. We'll explore three primary types of models: supervised, unsupervised, and semi-supervised models. Let's look at some key concepts and terminology in data science. Features, also known as attributes, are the individual measurable properties or characteristics of the data. They serve as the input variables that our model learns from. In our example of email spam detection, the features include email length, which refers to the number of characters or words in an email, number of emails from sender, which indicates how many emails have been received from the same sender, and historic open rate, which represents the percentage of previous emails from this sender that were opened by the recipient. These features provide valuable information that helps the model identify patterns in the data. The thing we are trying to predict is known as a label, also known as targets. They represent the output variable that the model is trained to determine. In our example, the target is whether the email is classified as spam or not, indicated by a yes or no label. By analyzing the features, the model learns to associate specific patterns with the label, enabling it to predict whether a new email is spam based on its features. The model essentially works to understand the relationship between features and labels in order to make accurate predictions. Supervised learning is one of the most common and straightforward types of machine learning. The goal of supervised learning is to teach a computer system how to make predictions or decisions based on past examples. To understand supervised learning, let's break it down using a familiar example: detecting spam emails. Imagine you're trying to teach a computer to recognize whether an email is spam or not. In supervised learning, we have two main components: features and labels. Features are the input data the information we use to make a prediction. In our example of email spam detection, the features include email length, which refers to the number of characters or words in an email, number of emails from sender, which indicates how many emails have been received from the same sender, and historic open rate, which represents the percentage of previous emails from this sender that were opened by the recipient. Labels are the output data, the answer we want the computer to predict. In our example, the label is whether the email is spam, yes, or not spam, no. Here's how the process works in supervised learning. We use this dataset to train our model. That just means that the model learns by finding patterns in the features that correspond to the labels. For example, it might learn that emails with a high number of links and certain keywords are often spam. So the key thing here that in supervised learning, we teach the computer to make predictions based on examples. We provide it with data that includes both the input data or features and what actually happened, the label, and the model learns to predict the output for new data. It's a powerful tool that helps us automate decision making and make accurate predictions in various fields. Unsupervised learning is another important type of machine learning, but it works differently from supervised learning. Instead of learning from labeled examples, unsupervised learning tries to find patterns and relationships in data without any predefined labels. This makes it particularly useful for discovering hidden structures in the data. A common application of unsupervised learning is clustering. Clustering is about grouping data points into clusters, where data points in the same cluster are more similar to each other than to those in other clusters. Let's break this down using an example. The unsupervised learning model analyzes the data and tries to find patterns or similarities. It looks for natural groupings based on the features. In our example, it might notice that certain customers have similar purchasing habits and group them together. The model then groups the data points into clusters. Each cluster represents a group of data points that are similar to each other. In our example, the model identifies 3 distinct clusters and groups them accordingly into purple, green, and red clusters. So in supervised learning, the model learns the relationship between our features and our labels, while in unsupervised learning, it identifies patterns on its own without the labels provided. Semi-supervised learning bridges the gap between supervised and unsupervised learning, combining elements of both to create powerful models with less labeled data. Let's explain this using a simple example. Imagine you want to train a model to detect spam emails, but you only have a small set of labeled emails where you know if they are spam or not, and a large set of unlabeled emails where you don't know if they are spam or not. First, you train the model using the small subset of labeled data. This is similar to supervised learning, where the model learns patterns from the labeled examples, e.g., emails labeled as spam or not spam. Next, you iteratively apply the model to the larger set of unlabeled data. The model uses what it has learned from the labeled data to make predictions on the unlabeled data, essentially guessing which emails might be spam or not. This approach is often called self-training. In self-training, you start by teaching the model with manually labeled data. Then, the model uses its knowledge to predict labels for the remaining unlabeled data, effectively creating a larger set of labeled data. By using semi-supervised learning, you can significantly enhance your model's performance without the need for a large amount of labeled data. This approach is particularly useful when labeling data is expensive or time-consuming, but you have access to a large amount of unlabeled data. We use different types of models depending on what we want to predict. We'll look through them in this section. Let's dive into classification machine learning models, which are fundamental in predicting categorical outcomes from predefined classes. This means we're trying to categorize data into specific labels or groups. For example, a model might classify whether an email is spam or not, whether a patient has a disease, or what objects are present in an image. In our spam example, we are trying to predict whether the email is spam. The possible results are yes or no. This is a binary classification problem as there are only 2 possible outcomes. If you wanted to determine whether a customer was happy, neutral, or sad, then you would have 3 potential classes. This would be known as a multi-class classification problem. There are several common models used in classification. We will go through these in detail later in the course to help you understand how they work. For now, we just want to know that when we predict classes, for example, yes or no, then we are using a classification model. There are loads of metrics we can use to assess the performance of a classification model. We will also review them in detail later in the course. Now, let's explore regression machine learning models, which are essential for predicting continuous numerical outcomes. Unlike classification, where the goal is to categorize data, regression focuses on forecasting or estimating numeric values. Regression models are designed to predict continuous numerical outcomes. This means we're trying to estimate a value rather than assign a category. For example, predicting the price of a house, forecasting stock market trends, or estimating future sales. There are a large number of different models we can use in regression problems and metrics we can use to evaluate their performance. We will discuss them later in the course in detail. For now, we just need to know that a regression model outputs a continuous numeric value rather than a class. Let's move on to clustering machine learning models. These models are particularly useful when you need to group data points into clusters based on their similarities without predefined labels. Clustering models work by organizing data into groups or clusters, where points within a cluster are more similar to each other than to those in other clusters. This technique is widely used for exploratory data analysis and pattern recognition. Clustering has a wide range of applications, including customer segmentation, anomaly detection, and image segmentation. There are a large number of possible clustering models we can use and a number of measures we can use to measure their performance. We will go through this in detail later in the course. For now, we just need to know that clustering is an unsupervised learning model, meaning it finds patterns in data without us providing the labels with the data. So, now we know that there are three types of machine learning. The first is supervised, where we provide the input features and provide the model with the answer, the thing it's trying to predict. It then learns the relationship between the input data and the label. The model is then able to predict based on past behavior. We also have unsupervised learning, which learns patterns in data without us providing the labels to the model. This is useful for clustering. Finally, we have semi-supervised learning, which combines both labeled and unlabeled data in training. This approach leverages the small amount of labeled data to guide the learning process, while also extracting valuable patterns from the larger pool of unlabeled data, leading to more accurate and robust models. Now, within that, we have three major types of models: classification, regression, and clustering. You can think of these as a subset of our overall model type. For example, a supervised classification problem may be our email example. Is it spam or not? We provide it with historic email data and inform the model whether that email was spam. It then learns the sort of things that would constitute a spam email. So, let's take our learnings forward. We will now look at the steps by which a machine learning model is built. The data you collect is the foundation upon which your model is built, so it's crucial to ensure that you gather the right data from the right sources in the right way. This process requires careful planning, domain knowledge, and an understanding of your specific project goals. Let's walk through the key steps together. Before you start collecting data, it's important to clearly define the problem you're trying to solve. Think about what the problem you're looking to solve is and what data may help you to do so. You'll need to utilize your domain knowledge to identify what data is needed and where it might be found. This knowledge can help you identify the right features, sources, and even understand the limitations of the data. You can think outside of the box here. It's not just your company data. Think about using open source data sets to enhance your own analysis. Now that you've gathered and prepared your data, it's time to dive deeper into it with exploratory data analysis, or EDA. EDA is a critical step in the data science process that allows you to better understand your data, uncover patterns, identify potential issues, and gain insights that will guide your modeling efforts. Let's explore why EDA is so important and what you should focus on during this phase. The first goal of EDA is to familiarize yourself with the structure and patterns within your data. This involves finding trends, identifying outliers, and exploring the distribution of your data. Next, you'll work to understand the quality of your data. This will help you to ensure that you are working with reliable data to make your predictions. Understanding the relationships between your features and labels is a key part of EDA. We'll look at correlation analysis, multicollinearity, and other feature interactions. All of the insight you gain during the EDA phase will help you to build a better, more accurate model. This is time well spent and is a critical part of your project. After completing exploratory data analysis, EDA, and understanding your data, the next critical step in the machine learning process is data preparation. This step involves cleaning, transforming, and handling any imbalances in your data to ensure that your machine learning model performs effectively. Proper data preparation can significantly improve the accuracy and robustness of your model. In this section, we'll explore the essential tasks involved in data cleaning, transformation, and managing imbalanced data. Data cleaning is the process of addressing imperfections in your dataset to ensure that your model is trained on high-quality data. One of the most common issues you'll encounter is missing values. These gaps can occur due to various reasons, such as data entry errors or incomplete data collection. You have two primary options for dealing with missing values: imputation or removal. Imputation involves filling in missing values with substitutes, such as the mean, median, or a value predicted by a model. On the other hand, if the missing data is sparse and not critical to your analysis, you might choose to remove those entries altogether. Another key aspect of data cleaning is identifying and handling outliers. Outliers are data points that deviate significantly from the rest of your dataset and can skew your model's results. Depending on your analysis, you may choose to remove these outliers, adjust them, or keep them if they provide valuable insights. Finally, data cleaning also involves correcting inconsistencies and errors in your data. This could include fixing typos, standardizing units of measurement, or resolving discrepancies in categorical data. Ensuring that your data is clean and consistent is essential for building a reliable model. Once your data is clean, the next step is to transform it into a format suitable for machine learning. Numerical data often needs to be normalized or standardized to bring all features to a comparable scale. Normalization typically scales the data to a range between 0 and 1, while standardization adjusts the data so that it has a mean of 0 and a standard deviation of 1. This step is particularly important for algorithms that are sensitive to the scale of the data, such as gradient descent-based models. For categorical variables, you'll need to convert them into a numerical format that machine learning algorithms can process. This can be done using techniques like one-hot encoding or label encoding. One-hot encoding creates a new binary column for each category, whereas label encoding assigns a unique integer to each category. The choice between these methods depends on the nature of your data and the algorithm you're using. Properly transforming your data ensures that your model can interpret and learn from it effectively. In many real-world datasets, you may encounter imbalances where certain classes or outcomes are underrepresented compared to others. For instance, in a fraud detection dataset, fraudulent transactions might be far less frequent than legitimate ones. If not addressed, this imbalance can lead to a biased model that performs well on the majority class but poorly on the minority class. To tackle this, you can use resampling techniques. Oversampling increases the number of instances in the minority class, while undersampling reduces the number of instances in the majority class. Alternatively, you can use more advanced methods. However you choose to do it, addressing imbalanced data is crucial for developing a model that performs well across all classes. As you move forward in your machine learning project, one of the most impactful steps you can take to improve your model's performance is to refine and optimize your dataset through feature engineering and dimensionality reduction. Feature engineering involves creating new variables from existing ones, transforming them, or combining them in ways that make them more useful for the model. Meanwhile, dimensionality reduction techniques simplify your dataset by reducing the number of features, which can help enhance model performance and prevent overfitting. Let's delve into these processes and explore how they can elevate your model. Feature engineering is the art and science of creating new features that can improve the predictive power of your model. This process begins with an understanding of your data and the domain knowledge that allows you to extract meaningful insights. One approach to feature engineering is creating new variables from existing ones. For example, if you're working with a data set that includes date and time, you can create new features like day of the week or time of day to capture trends that might affect your target variable. Another powerful strategy is combining features to create interaction terms that capture relationships between variables. For instance, in a dataset predicting house prices, you might combine features like square footage and number of bedrooms to create a new variable that reflects the size of bedrooms in a home. This can provide additional context that a model might find valuable. Feature transformation is also an important aspect of this process. It involves modifying variables to make them more suitable for modeling. For example, applying a logarithmic transformation to a highly skewed variable can help normalize it, making it easier for your model to learn from. While feature engineering is about expanding your feature set, dimensionality reduction focuses on simplifying it. Reducing the number of features in your dataset can lead to simpler models that are easier to interpret, faster to train, and less likely to overfit. One of the most commonly used techniques for dimensionality reduction is principal component analysis, PCA. PCA transforms your original features into a new set of uncorrelated variables called principal components, which capture the most important information in the dataset. By retaining only the most significant components, you can reduce the dimensionality of your data while preserving its essential characteristics. Another key aspect of dimensionality reduction is the elimination of redundant or irrelevant features. During your exploratory data analysis, you may have identified features that do not contribute much to the predictive power of your model. These could be features that are highly correlated with others or those that have little variance. Removing such features not only simplifies your model, but also helps it generalize better to new data. This step is crucial in avoiding overfitting, where the model performs well on the training data, but poorly on unseen data. When training a machine learning model, the process begins by feeding the training dataset into the model. During this phase, the model learns by adjusting its internal parameters, which are essentially the settings that control the behavior of the model to minimize the error. The error is the difference between the predicted outputs and the actual targets in the training data. After the model has been trained, it's important to check its accuracy to ensure it is performing well. This is done by evaluating the model on a separate validation set, which is a portion of the data that was not used during training. By calculating accuracy and other metrics like precision and recall, we can assess how effectively the model is making predictions. If the model performs well on the training data, but poorly on the validation data, this may indicate overfitting. Overfitting occurs when the model has learned the training data too well, including noise and irrelevant details, making it less effective at generalizing to new, unseen data. To combat overfitting and improve the model's performance, we can adjust hyperparameters. Hyperparameters are settings that govern the overall structure and behavior of the model. Fine-tuning these hyperparameters based on the model's performance during validation can lead to better accuracy and generalization. The process of training, validating, and adjusting continues iteratively until the model achieves satisfactory accuracy on both the training and validation sets, ensuring it can make reliable predictions on new data. Due to the iterative nature of this stage, it can take some time to perfect the output. In this section, we will explore how we measure the accuracy of machine learning models. We'll discuss various methods and metrics used to evaluate a model's predictions and ensure that it not only works well on the data it was trained on, but also generalizes effectively to new, unseen data. By understanding these evaluation techniques, we can better assess the reliability and effectiveness of our models. When evaluating the accuracy of a regression machine learning model, there are several key metrics that help us understand how well the model's predictions match the actual data. One of the simplest measures is mean absolute error, MAE. MAE calculates the average difference between the predicted values and the actual values. In straightforward terms, it tells us how much the model's predictions are off on average. A lower MA indicates that the model's predictions are closer to the true values, meaning better accuracy. Another common metric is mean squared error, MSE, which is similar to MA but with a slight twist. Instead of just averaging the errors, MSE squares each error before averaging. This means that larger errors have a more significant impact on the final result. MSE is particularly useful when we want to penalize larger mistakes more heavily. As with MAE, a lower MSE suggests better model performance. Building on MSE, we have root mean squared error, RMSE. RMSE is simply the square root of the MSE and has the advantage of being in the same units as the target variable, making it easier to interpret. It combines the benefits of MSE's sensitivity to large errors with an interpretable scale, providing a balanced view of the model's accuracy. Another important metric is R squared, R2, which explains how well the model's predictions fit the actual data. R squared is a value between 0 and 1, where 1 means the model's predictions perfectly match the data, and 0 means the model doesn't explain any of the variability in the data. A higher R squared value indicates a better fit between the model's predictions and the actual outcomes. Lastly, there's adjusted R squared, which is a refined version of R squared. It adjusts for the number of predictors in the model, making it especially useful when comparing models with different numbers of features. Adjusted R squared penalizes the model for adding predictors that don't significantly improve its accuracy, ensuring that we only add features that genuinely enhance the model's performance. A higher adjusted R squared indicates a more reliable model. When it comes to evaluating the accuracy of a classification machine learning model, there are several key metrics that give us insight into how well the model is performing. One of the most basic and widely used metrics is accuracy. Accuracy measures the percentage of correct predictions out of the total predictions made. It's a straightforward way to understand how often the model is getting things right. However, accuracy alone might not be sufficient, especially when dealing with imbalanced data sets where some classes are more frequent than others. To get a deeper understanding, we often use precision. Precision focuses on the quality of the model's positive predictions. It tells us how many of the predicted positive cases were actually correct. For instance, in a medical test scenario, high precision means that when the model predicts a disease, it is usually correct. High precision is crucial when the cost of a false positive is high. Complementing precision is recall, which measures the model's ability to identify all actual positive cases. It tells us what percentage of the true positive cases were successfully detected by the model. In situations where missing a positive case is critical, such as detecting a serious disease, high recall is essential. To balance both precision and recall, we use the F1 score. The F1 score is the harmonic mean of precision and recall, providing a single metric that balances the two. It's particularly useful when we want to ensure that neither precision nor recall is disproportionately affecting the model's performance. A higher F1 score indicates a better balance between precision and recall. Lastly, there's the receiver operating characteristic, ROC curve, and its associated metric, the area under the curve, AUC. The ROC curve plots the true positive rate against the false positive rate at various threshold settings, and the AUC summarizes the overall performance of the model across all thresholds. A model with an AUC closer to 1 indicates excellent performance, while an AUC closer to 0.5 suggests the model is no better than random guessing. In this section, we will explore a few different types of machine learning models and explain how they work at a high level. We'll focus on providing a clear, intuitive understanding of each model's general approach and purpose without diving into the technical details. By the end of this section, you'll have a good sense of what these models do and when they might be used without needing to worry about the complex mathematics or algorithms behind them. Now, we're going to talk about two fundamental concepts in statistics: simple linear regression and multiple linear regression. These methods are essential tools for understanding and predicting relationships between variables. Whether you're trying to forecast future sales, analyze consumer behavior, or even predict test scores, these techniques can be incredibly useful. Let's start with simple linear regression. This is the most basic form of regression analysis and involves just two variables: one dependent variable, which we're trying to predict, and one independent variable, which we're using to make that prediction. Imagine you're a student who wants to predict your test scores based on the number of hours you study. Simple linear regression helps you do exactly that by plotting your past study hours against your test scores and then drawing a straight line that best fits the data points. This line is called the regression line, and it gives us a way to predict your score based on your study time. Now, let's move on to multiple linear regression. This method is an extension of simple linear regression and is used when you have more than one independent variable. In other words, you're trying to predict the dependent variable based on multiple factors. Returning to our student example, suppose you want to predict your test score not only based on the number of hours you study, but also on other factors like how many hours you sleep and how many practice tests you take. In this case, multiple linear regression is what you need. Instead of fitting a simple line to your data, multiple linear regression fits a plane or even a hyperplane if you have more than two predictors. Multiple linear regression allows you to analyze complex relationships between variables and make more informed predictions. Random forests are a powerful and popular machine learning algorithm used for both classification and regression tasks. They work by combining the predictions of multiple decision trees to make a final prediction. Imagine you're trying to decide whether to bring an umbrella when you leave the house. You could ask a single friend for advice, like using one decision tree. But what if your friend is sometimes wrong? Instead, you ask a group of friends and go with the majority opinion. This is the basic idea behind random forests. Instead of relying on just one decision tree, a random forest builds many decision trees, each trained on a different random subset of the data. These trees are created independently. To ensure the trees are different from each other, not only is each tree trained on different data, but each tree also considers only a random subset of features, variables, when making splits. This randomness helps to make the trees less correlated with each other. When you use a random forest for classification, each tree in the forest gives a vote for a class, e.g., whether to bring an umbrella or not. The random forest then chooses the class with the most votes. If you're predicting a number, like house prices, the random forest takes the average of the predictions from all the trees. Random forests are usually more accurate than individual decision trees because they reduce the risk of overfitting, which is where the model is too closely tailored to the training data. Since they combine the opinions of multiple trees, they are less sensitive to the noise and variability in the data. They can handle both classification and regression tasks and work well even with large data sets and high dimensional data. In short, a random forest is like consulting a diverse group of advisors to make a well-rounded decision rather than relying on just one person's opinion. Let's take a moment to explore some key machine learning algorithms. Support vector machine, SVM, is a robust classification method that works by finding the optimal boundary or hyperplane to effectively separate different classes within the data. It's particularly useful when the classes are not linearly separable. Moving on to logistic regression, this is a statistical technique used primarily for binary classification tasks. It models the probability that a given input belongs to a particular class based on one or more predictor variables, making it ideal for problems like spam detection or disease prediction. Next, we have k-means, an unsupervised learning algorithm used for clustering data. It groups data points into k-clusters based on their similarities, with each cluster defined by its centroid, and the algorithm works to minimize the distance between data points and their respective centroids. Lastly, k-nearest neighbors, KNN, is a simple yet effective algorithm used for both classification and regression. It classifies new data points by looking at the majority class among the k nearest neighbors in the training set, making decisions based on proximity to existing data points. Each of these algorithms offers unique strengths depending on the nature of the data and the problem at hand. Depending on the model you choose, there will be differing levels of configurability and tunability. There are a large number of other models available. This was an introduction into some of the most common to give you a good grounding in the concepts. There have been some terms we've used here, which you can find definitions for in our attached article. It's always amazing how long data science projects take. From the outside, it can be hard to understand why. Here is an overview of the stages the project goes through and the challenges a data scientist will face. The first stage in a data science project is data gathering. This involves collecting data from various sources such as databases, APIs, web scraping, or surveys. The goal is to gather a comprehensive data set that will provide the necessary information for analysis. One of the primary challenges here is ensuring data quality and completeness. Data may be missing, outdated, or come from disparate sources, making it difficult to consolidate. Additionally, there may be legal or ethical considerations related to data privacy and access. Once the data is collected, the next step is data cleaning. This stage involves handling missing values, correcting errors, and addressing inconsistencies to make the data suitable for analysis. Common challenges include dealing with incomplete records, outliers, and discrepancies in data formats. Data cleaning can be time-consuming and requires meticulous attention to detail to ensure that the dataset is accurate and reliable. Data integration involves combining data from multiple sources to create a unified dataset. This stage requires aligning different data formats, resolving conflicts between datasets, and ensuring consistency. Challenges include handling discrepancies between data sources, merging data with varying levels of detail, and ensuring that the integrated dataset accurately represents the information from all sources. Exploratory data analysis, EDA, is the stage where data scientists explore and visualize the data to understand its structure, patterns, and relationships. This involves generating summary statistics, creating plots, and identifying trends or anomalies. The challenge here is to gain meaningful insights from the data and identify areas that require further investigation. EDA often reveals unexpected patterns or issues that need to be addressed before moving on to modeling. In feature engineering, data scientists create new features or modify existing ones to enhance the model's performance. This might involve transforming variables, combining features, or generating new ones based on domain knowledge. Challenges in this stage include identifying which features are most relevant, dealing with feature interactions, and avoiding overfitting by adding too many features. Model experimentation involves testing various machine learning algorithms and approaches to find the best model for the task. This stage requires setting up experiments, running different algorithms, and comparing their performance. Challenges include managing the computational resources needed for experimentation, ensuring reproducibility, and interpreting the results to choose the most promising models. Model selection is the process of choosing the best performing model from the experiments. This involves evaluating the models based on metrics such as accuracy, precision, recall, or F1 score. The challenge here is to select a model that balances performance and complexity, avoiding overfitting while ensuring that it generalizes well to new data. During model training, the selected model is trained on the dataset. This involves feeding the data into the model and allowing it to learn from it. Challenges include ensuring that the training process is efficient and effective, managing computational resources, and avoiding issues such as overfitting or underfitting. Model tuning involves optimizing the model's hyperparameters to improve its performance. This process often requires techniques such as grid search or random search to find the best combination of parameters. Challenges include the computational cost of tuning and the need to carefully balance the model's complexity to avoid overfitting. In the model validation stage, the model is tested on a separate validation dataset to assess its performance and generalizability. This helps ensure that the model performs well on unseen data. Challenges include choosing appropriate validation techniques, e.g., cross-validation, and interpreting the results to make informed decisions about the model's readiness for deployment. Iterative improvements involve refining the model based on validation results. This may require going back to previous stages such as feature engineering or model experimentation to address issues or enhance performance. The challenge here is to effectively manage the iterative process without introducing new problems and to ensure that each iteration adds value. Model deployment is the process of integrating the trained model into a production environment where it can make predictions on new data. Challenges include ensuring the model's compatibility with existing systems, managing deployment infrastructure, and addressing any potential scalability issues. With machine learning, one of the key challenges we face is the shifting nature of data over time. As market dynamics evolve, new regulations come into play, and trends shift. The data distribution that once trained our models may no longer represent the current reality. This change can lead to a decline in model performance, making regular retraining essential. By continuously updating our models, we ensure they remain relevant, accurate, and effective in their predictions. Another critical consideration in machine learning is the risk of bias. Models can inadvertently learn and perpetuate biases embedded in the training data, which can lead to unfair or discriminatory outcomes. To build ethical and responsible AI systems, we must proactively identify and mitigate these biases. This involves a thorough examination of our data and models to ensure that our predictions are fair and equitable for all users. Additionally, the complexity of some machine learning models, such as deep neural networks, presents challenges in interpretation. These models, while powerful, can be seen as black boxes because understanding how they arrive at specific predictions is often difficult. However, for these systems to be trusted and used responsibly, it is crucial to provide explanations for their decision-making processes. Ensuring transparency and accountability in AI not only fosters trust, but also helps in identifying and correcting potential errors or biases in the model's logic. Finally, adhering to data privacy regulations is non-negotiable in today's data-driven world. When collecting and utilizing data, especially personal or sensitive information, it is imperative to comply with regulations like GDPR and CCPA. This means implementing strong measures to protect data and ensuring that it is anonymized where necessary. By prioritizing data privacy, we not only meet legal requirements, but also build trust with users who expect their information to be handled responsibly and securely. Throughout this course, we've embarked on a comprehensive journey through the data science process, gaining valuable insights and skills along the way. We've covered the entire data science workflow, from the initial stages of data gathering and cleaning to the intricate details of model experimentation and deployment. In our exploration of models, you've learned about various types, including classification models that assign labels to data, regression models that predict numerical values, and clustering models that group similar data points. Each model type has its own strengths and applications, providing you with a versatile toolkit to address different data challenges. Additionally, we've discussed how to measure model accuracy using various metrics. You've become familiar with key evaluation metrics such as precision, recall, and F1 score for classification tasks, and error metrics like mean absolute error and mean squared error for regression tasks. Understanding these metrics equips you with the tools to assess and validate your models effectively, ensuring they perform well and provide valuable insights. Congratulations on completing the course, and best of luck with your future data science endeavors.